All right, and we're recording. Okay, so this unit is work, energy, power. So we're going to talk about work first and what it means to define work in terms of physics, not in what we think of as work, which we do very little of. So here we go. I don't like to do this, but I am strictly going to just read this. A body experiences a change in energy when one or more forces do work. So very simply, what we're going to realize is work changes the energy of an object. Specifically, we can talk about kinetic energy or potential energy, which we'll get to defining later. For work to have been done, an object must move from one place to another. That distance is required. So a force does positive work when the force and displacement are at least partially aligned in the same direction. Like if I push something and it moves to the right, if it moves in the same direction that I pushed it, I've done positive work. If a force causes no displacement, it doesn't move, it does zero work. And then you could do negative work if the force is pointed opposite the direction of displacement. The most common example of negative work is friction. If something's sliding to the right, friction points to the left. Those are in opposite directions. So negative work is done. Negative work would decrease kinetic energy, which will make sense when we talk about what kinetic energy is. Obviously, please do not write all of this down. Please. Paraphrase. Yep. There's going to be a lot of silence on this video.
Yeah. Why don't you get a camera and record the lecture?
I don't want to do that.
That'd be kind of sick. I'll be your camera.
It feels so weird.
Like the Bethel books online stuff.
So now I feel like about 2 minutes on one side. I feel like
I know.
just feel like I'm weird because I shower twice a day.
You are.
Just being honest.
All that means is that you.
That means y'all are. I'm not like.
It's not good for your
Y'all clean.
It's not good for your
No,
health.
it means that you stay more often than I do. You use too much
Right,
water.
that
and
hurts
you
your
got dry
hair
skin.
if it's hot water.
All right.
Just being honest. I mean.
Like, it's not okay.
So how do we calculate work? I'm not going to read that top paragraph. This is how we calculate work. Work is force times displacement times the cosine of the angle between them. So down here, if something is moving to the right and the force is directed up and to the right, there's an angle between your force and the way it's moving. That's the angle I use in my work formula. So in middle school, we may have talked about work if we ever talked about simple machines.
So R.
You may have seen, R is the distance. You may have seen work, force times distance. That's only if the force and the distance are exactly lined up with each other. If they're not, which I know real things aren't, if I push a table, I push down and to the right, then I have to take that into account by using the cosine of theta. And we'll really talk about where that cosine comes from. Maybe not today, maybe tomorrow. Now, this may not be what it looks like on our equation sheet, but it's going to look similar. It's either going to be FR cosine theta or FD cosine theta. I can't remember which one. The point is, it doesn't matter what letter I use there, as long as I know that stands for displacement. So I can go from this one, right? All right, so if I have a crane like you have over at the overpass on I-20. When a crane moves a load up, gravity does negative work because if the load is moving up, gravity points down, those are in opposite directions. So that's negative work being done. The crane does positive work because its force is in the direction of motion. When the load goes down, gravity does positive work, and the crane does negative work because now I'm just moving in the different direction, but my forces are still the same. It changes which one does positive, which one does negative work.
The
Nice.
force of tension is like that.
Yeah, that F would be tension. So it may seem like, why do I need to know whether it's positive or negative? It'll make more sense when we actually relate it to energy. Right now, we just have to know, how do I know if it's positive or negative? There is a ranking test that goes with it. I may pull that up on Wednesday, but that link does not work. All right, the only one I would write down here is the SI unit of work. The British CGS and atomic level, we don't use that. I'm not sure why it's on here. SI unit of work is the joule, Joule,
As opposed to,
as opposed to JUUL.
never met her.
She's a fickle mistress.
Ah, yes, indeed.
You'll notice that if I multiply force times distance, the units for those are newtons times meters. So basically, any unit we define in this class is some combination of kilograms, meters, and seconds. I can boil it down to those three units. A joule can be broken down into 1 newton times 1 meter. And of course, I could break a newton down even further, but we won't do that because it's just a waste of time right now. No, not quite that. Point is, we measure it in joules, which we just say is a capital J. All right, first problem. A droplet of water has a mass of 50 milligrams and it falls at constant speed under the influence of gravity and air resistance. After the drop has fallen 1 kilometer, what's the work done by those two forces? First, what's probably a good thing to do?
Draw the free body.
Draw that free body diagram. What forces are on the water droplet?
Gravity pulling it down.
That force of gravity.
And resistance pulling it up.
We can say the force of air pointing up.
Fair.
Yep, it's pretty fair. Which way is the droplet moving?
Downward.
So that's actually pretty important because it tells me which one of these is going to do positive, which one's going to do negative work. So the work done by air resistance, or wear, how are we going to calculate that? Well, our formula for work, FR cosine theta. So I need to know, basically, what is the force of air? What is R? And what's the angle between its direction of motion and that force of air? Which of those do I actually know currently? So I know displacement is 1,000 meters. 1 kilometer, I have to change it to meters. What else do I know?
The mass.
The theta? No.
So, yeah, we know the angle, actually. Oops. What is that angle?
It's gonna be about 180.
So it's moving down, air points up, the angle between those is 180. And actually, that's where the negative comes from. If I take cosine of 180, it's negative 1. Yeah? So that's what's going to make this work come out to be negative. The question is, what's that force of air? How would I figure that out?
By equating it to the force of gravity.
we're moving at constant speed, so these forces are the same. How do I figure out the force of gravity? Mass times gravity. But the mass needs to be in kilograms. So what's 50 milligrams in kilograms? I need more room. Yeah, there's quite a few zeros there. So this would just be grams. And then kilograms would be 3 more zeros. So this is milligrams to grams, kilograms. This is one where scientific notation may be useful, but I don't like writing it. Plus, I'd much rather plug just a decimal into the calculator than scientific notation. So the force of air resistance is whatever that number ends up being, which is really small, which is 0.00049 newtons. So I'll put that for the force of air. And now solving for that work done by air, which I probably should have done A first, which is gravity, but oh well. Times 1,000. We get the work done by air is negative 0.49 joules. So that was technically B. The work done by gravity will be the force of gravity times displacement times cosine of the angle between that force and that displacement. What's the force of gravity? Same thing as the force of air. We just found that. Displacement was 1,000. What's the angle this time?
0.
They're in the exact same direction, so it's 0, which turns out to just be 1. So we end up getting the same thing. Oops, not negative. It is positive 0.49 joules. So if it's not speeding up, the work done by these two forces should cancel each other out. There's something called net work, which we're going to define in a little bit. The net work here would be 0. Any questions on that? We're kind of just using the formula. But we also have to think about, in the free body diagram, the direction of the forces and which way it's moving. Next, one more. Oop. All right, this one has a few more steps. A sled loaded with bricks has a mass of 20 kilograms. It is pulled at a constant speed by a rope inclined at 25 degrees above the horizontal, and it moves a distance of 100 meters on a horizontal surface. If the coefficient of kinetic friction between the sled and the ground is 0.4, calculate these 3 things. Well, this problem escalated quickly. Indeed. First, maybe a quick sketch. If that's the sled loaded with bricks, what's happening to it? It's being pulled by a rope that's at 25 degrees. And we'll say it's to the right, just because that seems natural. So first thing is I probably want to draw, again, that free body diagram. So I'll take the easy ones. Force of gravity, it's on the ground, so there's normal force. What 2 other forces are there? Tension, which I have to draw at that angle, which is 25 degrees. And then there's friction, which is to the left. So fun fact, if we're drawing a free body diagram as part of our answer on the actual AP exam, I would just draw this. I know we're going to have to split that tension up into two parts, but you're not supposed to do that on your official free body diagram. So instead, I'm going to draw it again. And I know that I can use these forces because none of them are at angles. But then what do I have to do? I have to split the tension up into its x. And its y. So we'll talk about how to do that in a second. Once I got my free body diagram, how am I going to solve for a specific force? Back in the last unit, what was the next step after I drew the diagram? Bueller? Maybe I'll give you a hint. Let's write our net force equations. Well, in this case, it would be equal because it's constant speed. But I still want to write it like this because they're not always equal. So in the x direction, what forces do I have?
Force of tension and force of friction. Or force of friction and force of tension.
So in the positive direction, I've got the x component of the tension. Basically, how much is that rope pulling to the right? In the opposite direction, I've got friction. Let me make more room here. And it is moving at constant speed, so what's this equal to? 0. Which makes those two forces equal to each other. What about my y direction?
Normal force, the force of tension Y, and the force of gravity.
So normal force and that y part of the tension both point up, so I add those. We'll subtract gravity, and again, this should be equal to 0 because the sled isn't moving up or down. So, which side do you think would help us solve for the force of tension? The right or the left?
Right.
All right, let's start there. There's no specific equation for normal force. How can I rewrite that y component of my force of tension? If the force of tension is at 25 degrees,
Sine.
the y component would be that tension times the sine of 25. Just like we broke up the velocity and projectile motion, do the same thing here with forces. That means the x would be tension times the cosine of 25, if I have to use that, which I probably will later. So instead of writing FTY again, I'm going to write force of tension, because that's really what I'm looking for, times the sine of 25. And then how do I find the force of gravity? Well, let's, for right now,
Is the weight plus the weight times gravity.
do what?
The mass times gravity.
Mass times gravity, which I do know those two numbers, but I'm going to keep it mg for now, because that may cancel something out later. Maybe. I do know mass and gravity, but I don't know the normal force. So can this equation alone help me find tension? No. So what does that mean?
We use the other one.
I got to go to the other one. So we just said the x component was tension times the cosine. And we'll go ahead and put the angle in, because why not? How do I find friction? Yep, I heard coefficient times normal force. So I do know the coefficient is 0.4, but again, I don't know the normal force. So I can't use that one by itself to solve for tension. So now I've got two equations. How do I use them both together to help me figure out the force of tension?
Equal each other.
So there's several things I can do. I could solve for normal force and then plug that into the other one. Or how would you do it? That's my first thought. If they both equal 0, did someone say that?
Yes.
Then let's try setting them equal to each other. I'm going to go ahead and plug in the numbers that I know. So the mass is 20, G is 10, so I'll go ahead and say that's 200, if that's not a stretch. Mg is 200. Now what?
You can cancel out
What could I cancel out?
normal force.
Can I?
Wait, no, never mind.
You can always try to isolate something.
So what should I isolate?
You want to find normal force, normal force.
You want to isolate normal force? All right. So how do I isolate the normal force?
Subtract force tension cosine 5
I'm saying subtract this.
on both sides.
So if I subtract that ft cosine theta from both sides, then I've got normal force plus tension sine 25 minus 200 minus tension cosine 25.
The other normal force over there.
How do I get this over here?
Subtract from both sides.
Subtract it so I get negative 1.4 times the normal force. Man, this is a lot of work. Then what? This probably wasn't the fastest way to do this problem.
Yeah.
But now we're already too far in the rabbit hole. So how do I get normal force by itself? So divide every single thing by negative 1.4. So I'm going to do a couple things here. The sine of 25 is 0.42. So if I divide that by negative 1.4, you get negative 0.3 times the force of tension. So I did the sine of 25 divided by negative 1.4, and I got that decimal. 200 divided by negative 1.4 is 142.9, and then cosine of 25 divided by negative 1.4 is negative 0.65. All right, what's next? Combine. Let's combine those tensions to be one term. So that's negative 0.95 force of tension plus 142.9. All right, that's as far as I can go solving for normal force. Yeah, you did not have room on your paper to do this. So now what could I do with this? I don't know. I know Danny's kind of led us down this trail.
So you're telling me you can't use it off that?
No, you can.
I mean.
The question is, what do I do with that now?
It's equal to 200, right?
What's equal to 200?
Negative 0.95 force of tension plus 142.9. This is a normal force equal to a force of gravity.
So, not exactly. Because you're also pulling up on it with the rope. But let's look at that equation I just circled. I know what normal force is in terms of this mess. Substitute that in for normal force. So we're going to... Nope, we're not. I'm going to have to erase this in a while, but moving this way. If I take this equation, I could use either one to be honest, and I go ahead and figure out, well, instead of normal force, I'm going to plug in negative 0.95 force of tension plus 142.9. Are we cool with that? Then I'm going to add, what's the sign of 25? 0.42 times the force of tension. And we already said mg was 200. Now I only have one thing I don't know, and that's the force of tension. So we were going to have to do this all along. We just probably took the longest way to get there. So I've got two force of tensions, though. How am I going to combine those? Through combination. I'm going to have to take the negative 0.95 and add 0.42 to it. And you get negative 0.53 times the force of tension. And then these are just straight numbers. So positive 142.9 minus 200. Yep. Is negative 57.1. Well, now we're getting somewhere. What's next?
Do you isolate the force of tension? Or
Divide by.
Yeah. Basically now we're just solving for FT.
was involved.
It was. It was way more complicated than it needed to be.
Yay.
You
Was
made the
that just
question.
for part A?
That was just part A. Yep. And now, see, this is how AP Physics goes. We work a problem, we get an answer, and I'm like, why is that negative?
Didn't you make this problem?
No, I did not.
No, you can't even-
Did I really make
Why is it
anything?
100?
Do what?
No, that's what I'm being stupid.
Oh, okay. No, I was gonna say something, Mr. Williams. When you did something.
Okay.
No, when you solved for the force of tension on the one of them, you put negative 0.65, but you divided by a negative. So wouldn't that?
Oh, see, that's what I
Plus.
was wondering. I just trusted.
Oh, talking about right here?
Yes, so that's what I was wondering that, and then I was like, maybe he's.
Well, okay, this whole answer is wrong then.
So I didn't want to call you
Yay!
Because usually bald people do things in
All right, that's just going to change this number.
It's not my fault.
So instead of 0.95,
I noticed that.
that's actually a positive,
Yeah, telepathy. That's what I noticed. It didn't say anything.
a positive 0.35. It's going to go. Stop it.
Yeah, I didn't want to be wrong,
Yeah.
but I was like,
Apple pen battery.
So that's going to go there.
would that make it not negative? Now?
Yes, it would.
Dope.
So that's going to be
Batatas.
0.77 FT. Yeah, 0.35.
It is 0.35.
So now we get 74.2 newtons and positive, which should make sense. I made a mistake. I didn't change the sign of that when I divided by the negative 1.4.
The 53 becomes 0.35?
Yes.
No, it becomes 0.77.
Yeah, the only thing that changed was the coefficient times the tension. Okay. Yep. All right. Well, so I need to write that down before I erase it because I need more room.
Yeah. There's.
Are we solving for part B now?
Yeah, that was part A. Okay, now that we have part A though, part B and C are gonna go like that.
I hope so. Because we have all
Let's
the.
take the long
We
way.
have most of
Part
them.
A should have gone like that too.
So is that all we had to do to find part A? Or did
All-
we
is
have-
that
Is that all we had to do?
Is that all we had to do?
Like the, you know how you.
Yes, that's all we had to do.
Like, did we have to go through all that to get? Like,
So we were gonna have to do some substitution. It just didn't need to be this long.
Okay. That's not-
Um, I could have just taken one of these and solved for the normal force and put it in the other one, and it would have been a lot shorter. But both ways would give you the exact same answer. It's just we took the road less traveled by.
How do you know it's the road less traveled? I think what you meant to say was the more confusing road.
Which is usually the road less traveled.
That depends on who's
The
traveling.
off-brand Danny version.
All right, here we go.
So if you like to drive 10 miles instead of 2. That's basically what she's saying.
Oop.
I just got that.
You're not blind.
Probably not.
Come on. What the heck?
My elevator does not go all the way up today.
I don't know what that means.
Okay, here we go.
If I said to you, you said something, and I said your elevator just doesn't go all the way up.
All right. What was the tension again?
74.2.
74.2. All right, work done by the rope is the force. Well, we'll go ahead and say FR cosine theta, but the force here would be the tension because it's the rope. How far was this drug? 100 meters. And then what was the angle between the rope and the which way it was moving? That was 25 degrees. So I wasn't lying. This is all we have to do. Once we have the force, I just plug it in the work formula.
Stop that incessant tapping.
which turns out to be a lot of joules.
Hello.
School gun conference game.
My mom.
It's not quite hellijoules. It's
What's
kilojoules.
the displacement? Oh, 100.
Yep.
Like Ghostface Killer?
All right, so lastly, work done by friction is the force of friction. Well, actually, let's think about this. In the last problem, we found the work done by air resistance and gravity was the same because it was moving at a constant speed. Is this also moving at a constant speed?
Yes.
Yes. So if the rope does positive 6,724.8 joules, what's the work done by friction?
Negative.
Oh, 6,724.
That one was pretty simple too.
Man, that A though.
Yes. So B and C, easy as pie. Part A,
Alright, it's fine, it's just a number.
well, yeah, now that all that
E20.
background is taken care of.
That since you can't get help when you're taking the AP exam, I think I'm going to fail it.
You'd be surprised.
I'm going to do it.
You'll be surprised.
I'll find out every question.
I'm gonna get that.
Don't be rude. Like, just seriously, do I look like?
Okay.
All right.
Before I'll keep the bus.
I'm going to skip that pulley stuff.
You look like my grandfather's stuff.
Yeah, we don't have time to start this.
I knew you were gonna say something.
Something. No, you look good.
This is where I'm going to start the video tomorrow.